Hello, so we have a question, number 10, nope, sorry, chapter 10, number 28, talking about a ball rolling with an initial velocity of 8 meters per second, rolling up a hill without slipping. Kind of hard to envision this, so let's just try my little ramp. I have a ball, the ball's rolling up the hill. It will roll up the hill until it stops rolling up the hill, and then it will stop and then potentially roll back down again. So our question is, if it's initially rolling at 8 meters per second up a hill without slipping, what will be the vertical height it reaches? How high up the hill will it go? So what do we have? We have a situation where at the, let's see if I can get the board in here pretty well. At the top of the hill, let me mark off my edges here, and over here. At the bottom of the hill, it has both linear kinetic energy and rotational kinetic energy. And then it's going to go up the hill until all that's left, or all it has, is gravitational potential energy, mgh. So at the bottom of the hill, it has 1/2 mv squared. It also has 1/2 I omega squared. And then it's going to roll until those both disappear, and all that remains is mgh, gravitational potential energy. Moment of inertia for a spherical shell is going to be 2/3 mr squared. And then there's a standard substitution we've been doing. We say V equals R omega, so omega equals V over R. So when we make those substitutions, we'll say 1/2 mv squared plus 1/2 times 2/3 mr squared times V over R squared is V squared over R squared equals mgh. I know that's kind of a mess, but it's all in there. This is the equation we're looking at below the line. So, below the line, mass cancels because it appears in every term. And then conveniently enough, over here, radius squared cancels. So we have 1/2 v squared plus 1/2 times 2/3, 1/3 v squared equals gh. What we're looking for is the height. So the height that it reaches, height equals 1/2 v squared plus 1/3 v squared, 0.833 v squared divided by g. 0.833 times 8 meters per second squared divided by 9.8 meters per second squared. Should have my calculator out and ready, but I don't. 8 squared is 64 times 0.833 divided by 9.8 gives us 5.4 meters. That's the height that the ball will roll to. The second part of the problem roll without slipping. The second part of the problem, the ball's going to slide up the hill. It's going to slip, or it's actually exactly the same situation as if we just threw it straight up in the air. It's just a case where linear kinetic energy turns into gravitational potential energy. So 1/2 mv squared equals mgh. Mass cancels. H equals 1/2 v squared divided by g. 1/2 times 8 meters per second squared divided by 9.8 meters per second squared And this time, 8 squared divided by 2 divided by 9.8, we get 3.3 meters as the maximum height. That seems weird to me. So slipping, or throwing it straight up, doesn't go as high as if it was rolling. But the fact of the matter is that when it was rolling, without slipping, rolling at 8 meters per second, it already had more energy because it had both linear kinetic energy and rotational kinetic energy combined. Both of those energies were converted into gravitational potential energy, and that was higher than if all we had was linear kinetic energy, and that was converted into gravitational potential energy. So that is number 28 from chapter 10.